Hello, we're starting on topic 6, and that's an important change from what we have done before, and this is concerning memory elements. See, what we have done so far is all the circuits we have discussed were regarded as combinational. Combinational meaning that the present input is the only thing that affects the output. That means the output only depends on the present input. No history of what has happened in the past is ever remembered by a combinational circuit. The circuits we will be designing have the capability of making decisions. See, you cannot make a decision if you don't have a memory. Memory means this, means that something of the past is remembered based on those in the past. You have to make a decision. You will be made those based on what has happened in the past and what is happening now. You will make a decision. None of the circuits we have discussed so far are capable of doing this because they only have the present input and nothing is remembered from the past, and based on the present input the output is decided. Okay, what we'll be doing now is talk about memory elements. We are not going to be talking about a big circuit with a lot of memory and so on. Instead, what we'll be doing is we'll be talking about a simple little circuit that does remember something. See, this is my first goal. I want to show you something. I want to build a circuit that does remember something. Once I'm able to do that, then what I can do is use that little circuit and start extending it. Start doing more things to it. Okay? And orient it the way I want it, the way I like to see memory represented. All right, so let's first talk about combinational versus sequential circuits. We'll be doing that. And once we do that, then we go into that basic element that I was just talking about. Okay? Something that remembers something. And then we go into more advanced memory elements. Then we say, let's also make it so that it keeps the time. Let's also make it so that it has several inputs for initialization. It has things like that. But then the big thing, the important thing is that little element that does remember something. Let's talk about sequential and versus combinational. Look on the right hand side. What I have is a combinational circuit. It has a function, right? It has a function, and the function that this combinational circuit has, it takes the present input, let's say J, and produces a certain output. Now, that certain output is for this particular input. You leave the circuit as is, come back tomorrow, give it the same input, it gives you the same exact output. Okay? And between this input and and then between today and tomorrow, you give it a million other inputs, but then when you come back tomorrow, give it that same exact input, it's going to give you the same output. What I'm saying here, the combinational circuit doesn't keep a history of what has happened to it. Doesn't keep a history. It has no memory to keep a history. So it doesn't keep history. It has no memory to keep history, and therefore it cannot make decisions based on the past events. Nevertheless, it's a good circuit, this combination. Look at what I have on the left-hand side, though. What I have on the left-hand side is, what I'm showing is the present input is not necessarily, let me write this down, not necessarily, or the present output is not necessarily the function of the present input only. Okay? I'm not saying doesn't have a role. It does have a role, but then there are other participants here as well. So what I can write is this. Actually, this is more like reality. The present output is a function of that same function of the present input, an input a second ago, an input 2 seconds ago, an input 3 seconds ago, and inputs since my circuit was ever created. Okay? Since the day my circuit was created, I keep applying input to it, and my circuit remembers, and then today I give it an input, it remembers everything that has happened, and based on that will provide the output. See, that's really not possible. So it is, the memory cannot be so large. Okay? But then, symbolically, this is what we are saying. But then, I say the present input is, the output is a function of the present input and the old output. Instead, I'm sorry, the present input and the old inputs. Instead of saying the old inputs, let's kind of formulate this and say that the output of my circuit is a function of the present input and the present state of the circuit. State being accumulation of all important events that have happened to the circuit. It works exactly like we do, right? We make a decision based on what happens now and the state of our mind. Okay? The state of our mind is used in making a decision today based on what happens to us. Okay? Maybe the state of my mind is I'm going to take a bus, okay, to go somewhere. Or the state of my mind is to go somewhere. And the means of transportation is the bus. A train arrives. That's the present input. I'm not making a decision based on the train. I'm going to make a decision based on what I am thinking, and therefore I will not get on the train. I will get on the bus when the bus arrives. Okay? So I have something in my mind, and what input happens, I make based on that something in my mind, and that input I will make a decision. And the circuit does exactly the same thing. So I say, I'm not going to write W as it being a function of the present input and unlimited inputs of the past. Instead, I'm going to put all those inputs into the state of the circuit and say, my output of the circuit is going to be based on the present input of the circuit and the present state of the circuit. Okay? But when the present state of the circuit is used for determination of the output, that present state of the output of the circuit also changes. Okay, so my state of this circuit mind is that I'm waiting for a bus. The bus arrives, I get on the bus. So the state of my mind has changed now. I am on the bus. And therefore, any input that happens, not only I make a decision, also the state based on which I made the decision, that is going to change also. So instead of having one equation or one function, I have two functions. The present output is the state is a function of the present input and the state of the circuit. The state of the circuit changes. The next state of the circuit changes. That next state of the circuit, look at the plus I put here. That state of the circuit changes, Si plus 1, based on the function of the present input and the old state of the circuit. If you just look at these two statements here, I'm clearly talking about the feedback. See? We have feedback in our mind, in our brain. Because something happens, that something feeds back in our mind, and our decisions are based on those feedbacks. And then the feedback is very clear here. Look at this, the representation of S, W, and J in this circuit here. J comes in, decides on something for the output. That decision is based on the input. Let me use a different color pen. That output is a function of the J input and the present state of the circuit, which is this thing over here. And then, as this output is being worked out, is being decided, something else is going to happen, and the same input and the same present state participate in determination of the next state of the circuit. Why do I say next state of the circuit? Because that next state is the feedback that goes back and makes a decision for the next input that arrives. Okay? And this is a sequential circuit. The sequential circuit has a feedback. And if I want to make a sequential circuit, I have to make it with some feedback. Something we have not seen so far. See, whatever we have seen so far in our circuit, this is an AND, this is an OR. The NAND is connected to the NOR is connected to some other circuit, some other gates and all that. We never did something like this. And actually, something like this is what decides that my circuit has memory. There is a feedback. The number of feedback lines decide how much memory my circuit has. See, a single binary line can remember 0 or 1, or can distinguish 0 or 1. So if I have a circuit like this with one feedback, that circuit can only distinguish two things from each other. And these two things are decided by the 0 or 1 on this feedback. Okay? If I have more feedbacks, if I have 3 feedbacks like I'm showing here, I can have up to 8 different things that my circuit can remember. Not that it's always going to go to 8 different things, but potentially can remember 8 different things. That means my circuit has 8 states. And each state is what has been accumulated from the past. If I have 10 lines, I have up to 1024 different things that my circuit can remember, potentially. I'm not going to do 10 lines. I'm going to do only one line. I'm going to create a feedback and then show you that that feedback remembers something. My circuit with that feedback remembers something. Let's build a circuit with a single feedback. I have an R, I have an S, okay? These are my inputs. Why I've named them R and S, don't worry about it for now. Then I have an output Q. And then I have a feedback Y that goes back into the circuit. These are two NOR gates. I'm going to take the upper NOR gate and kind of pull it forward, okay? Or the lower NOR gate and kind of push it back. I'm going to redraw this circuit in this fashion shown below. This is the same exact circuit. The circuit up there has one feedback. The circuit below has also one feedback, even though you see crossed. Okay, but that's okay. It's still the same circuit. There is only one feedback line. This is the feedback model of these two NOR gates, and down below this is called cross-coupled NOR gates. Someone decided this looks nice many years back, and it is now customary that we draw it this way and we analyze it this way. The good thing about this model is that you can call this one the output and this one the feedback, or the other way around. You can call this one the feedback and this one the output. It doesn't matter. And actually, if you look at the circuit on top, if I push the lower gate back and then push this one forward, that becomes the feedback. Q becomes the feedback. Okay? So this cross-coupled structure is something that I claim that it has memory. Okay? It doesn't have a lot of memory. It only has one little thing that it remembers. Let's see what it remembers. Okay? I'm going to start with... notice that from here to here, I was using Y. I'm using Q bar. Don't worry about that. For now, I call it Y. Okay? And I call it Y. For now. I'm going to start with SNR 0, 0. I'm going to propagate this to see what I end up with. Actually, in order to propagate this, I have to make a decision as to what is my initial state. I start with the 0 initial state, okay? Or the 0 present output. So I'm starting with 0, 0, 0. Okay? If I start with 0, 0, 0 on S, R, and Q, Q is a 0, goes to the lower NOR gate. S is 0, goes to the lower NOR gate. And therefore, Y is presently 1. And therefore, this is what I'm starting with. Don't look at Y for now. Okay? I only want to show you relation between S, R, and Q. At a later time, S changes to 1, R remains 0, and let's see what happens to the rest of the circuit. S has changed, and therefore the lower NOR gate sees a change on the input, and therefore it's seeing a 0. And then the Q output is still a 0, and therefore 2 zeros for the NOR gate cause the output to become 0. Y to become 0. Since Y became 0, it feeds back to the upper gate, and therefore now I have a 0 here. Now I have a 0 here, and therefore what I have here is a 1. Okay? And then the circuit stays stable. So what happens is, as soon as S becomes 1, following that, first thing that happens, Y becomes 0, and then Y becomes 0. Let's show it this way. S became 1. As a result, Y became 0. Y became 0. As a result, Q becomes 1. Okay, with a delay, with a small delay. Those are the gate delays. And now I'm sitting at the situation where I have a 1 on S, a 0 on R, a 1 on Q, and by the way, the Q Y output or the Y feedback is 0. Okay? Things change, and at a later time, I will set my S that was 1 back to 0. Okay? Now, S has seen a change, and therefore the gate that I process is this lower gate. Anytime you make a change in the circuit, the gate that sees that change, that's the one that will be processed. That changes, and therefore, let's look. I have a blue 1 on top, and then I have a 0 here, and the output remains a 0 of the lower gate. The 0 feeds back to the upper gate, so I have a 0 here, and then I also had a 0 on R, and therefore the 2 zeros keep my output Q at a 1. And therefore what has happened is nothing. Okay? S changes to 0. R is still 0. This is still remains 0. This is still remains 1. Let's go further. What's going to happen now is I'm going to change R to 1. Again, as soon as I change R to 1, I keep S the same. Okay? As soon as I change R to 1, the gate that sees that change is the first one that reacts. Which one sees that? The upper gate reacts, and therefore the 1 on R immediately seen by the upper gate. The upper gate now has the upper gate has a 1 on its upper input, a 0 on its lower input. That one, the 1 and the 0, cause the output to become 0. And therefore, by this becoming 1, okay, by R becoming 1, Q changes to 0. And then what happens is Q changes to 0. Q changes to 0. I have a 0 here. I have a 0 on the lower input of the lower gate. Also, 2 zeros cause this output to become 1. And therefore, once Q becomes 0, then Y becomes 1. And therefore, I end up with a 0 here, a 1 here, a 1 here, and a 0 here. Okay? So the circuit continues like this. And then later on, I go back and change my input R back to 0, S back to 0, going back to the initial state of the circuit. R has changed, and therefore the gate that reacts to it is the upper gate. Okay, so I have a 0 here. The upper gate reacts to this. 2 zeros on the 2 inputs of the OR gate. The output right. No, actually, I forgot to propagate the green one over here. Okay, so when my R changes from green to the brown 0, the upper gate sees a 0 on its input, and then the lower input is still green 1, and therefore the output of the NOR gate, since there is a 1 there, it remains as 0. That 0 propagates back to here. This is 0. The S is also 0. And therefore, the lower NOR gate has 2 zeros on the inputs, and therefore the output remains as 1. And therefore, what I have here is a 0, is a 0, is a 1, and is a 0. Okay? I claim that my circuit has memory. Okay? The reason is this. Initially, on this side, don't look at Q, don't look at Y, look at this. I have S is 0, Y is 0, Q is 0. At a later time, S is 0, R is 0, the same thing. S is 0, Y is 0, R is 0, the same as the orange area. But then look at the output. The output is 1. In one case, S and R of 0, 0 are giving me the output of 0. In another case, S and R of 0, 0 are giving me a 1 on the output. What is this? Well, this is a memory element. The circuit remembers. What does it remember? I'll talk to you about that. It remembers something. That's what counts. It remembers something. Actually, what my circuit remembers is whether the last positive pulse means a pulse that goes from 0 to 1 back to 0. The last positive pulse was on S or was on R. If the last positive pulse was on S, as a result, the output is set to 1 here. The last positive pulse is on S, and therefore the output is set to 1. If the last positive pulse was on R, here is the last positive pulse is on R. The output is 0. Okay? So my circuit remembers something. Remembers whether the last positive pulse was on S or the last positive pulse was on R. The output, when I look at the output and I see a 0, I say, oh, the last positive pulse must have been on R. That's why my output is 0 or my output is reset. If I see a 1 on my output, I say, okay, the last positive pulse must have been on S or on set. That's why my output is set to 1. And therefore, this S is for set, R is for reset. Okay, look at Y that we've been ignoring. We've been kind of hiding it. Okay, look at Y. Y at all times is the complement of Q. Okay, that's why I call Y Q bar. I could do this same exact analysis with considering Q being the output. So if I just turn the circuit around, Q becomes Q bar becomes Q, S becomes R becomes S. So it doesn't really make any difference which one you call your output, which one you call your feedback. Or both of them are your outputs. If you like the Q output, or if you want the active low output, use Q bar. Okay? What I've shown is my circuit has memory, and that's important. That is important. My circuit has memory. And before leaving this, I like to draw my orange area a little bit better. Okay? This is a circuit with memory. I call this one SR-Latch. It latches S and R. Okay? Before we go further, let's do Verilog. I can do Verilog description of this by having two NOR gates and wire them together. It works. Okay? Or I can write an assign statement for Q and for Q bar. I can do this. I can say assign sharp sign, let's say 3 nanoseconds. I have to have the delay. Q equal what? Equal NOR of R NOR Q bar. I'm calling this one Q bar. And then I have another assign statement. Assign. Let's give that 4 nanoseconds. Q bar equal NOR of S Q. That works. Okay. Instead of doing this, we can use an always statement for describing this, and usually people use always statements. We don't do this very often. The only time we do this is when I want to show you that there is a feedback here, and the feedback is actually there, and the feedback is what saves the causes the memory. Okay. Always at when S changes or when R changes, if S is 1, okay, Q becomes 1, else if R is 1, Q becomes 0. That's all. Okay? That's all there is to it. Let me write it down here. Module. SR-Latch. Input S, comma R output reg Q. Why reg? Because Q has to retain the old value, and because Q is being set inside an always statement. Then I say always when S changes or when R changes, flow begins. When flow begins, if S is if S is 1, Q becomes 1, else if R is 1, Q becomes 0. And I don't really need an end statement for my always, but then I do have to have end module. And this is the Verilog description of this little circuit, which we refer to as SR-Latch, and this is the basis of our memory components. All right. So far, that's all I have done. I've created an SR-Latch. Let's characterize this. The circuit is a circuit with S and R inputs. I showed you the very long description here, but then I'm showing you here a transition table. Look, what I have here is if, look at this. If S and R are 0, 0, Q is 0, okay? Q plus is 0, okay? Remains the same as Q. If S and R are 0, 1, Q plus becomes 0. That means you are resetting it. You're forcing it to 0. If SR is 1, 0, let me use the proper coloring. If SR is 1, 0, you are setting it to 1. Okay? You are setting it to 1. You are resetting it to 0. You are resetting it to 0. Okay? But then if you are not changing anything, that means your S and R are 0, 0. Q remains the same and remains 0. Okay, so this is no change. This is no change. Okay, so this is no change because S and R are 0. This is set. And this is reset. I've been avoiding 1, 1. Actually, you see avoiding 1, 1 in many different places. Look, in here, in the timing diagram, I never showed you 1, 1. Okay? In my Verilog description, this one down below, you don't see 1, 1. Why you don't see that? Look, I say if S and R, there is an event on S or R. Okay? If S or R changes, flow begins. If S is 1, Q is 1. Else, if R is 1, Q is 0. I intentionally made it else if. I didn't put two statements here, meaning that if if S and R are simultaneously 1, I am avoiding it in this Verilog description. In this timing diagram, I also avoided that. Actually, what happens is the reason my circuit remembers something is because either Q is 0, Q bar is 1, or Q is 1, Q bar is 0, like a flip. If I give S and R both 1s, my Q and Q bar become the same value. Okay? What it means is my circuit forgets whatever it remembered before. It doesn't remember whether Q was 1, Q bar was 0, or Q was 0, Q bar was 1. No, Q bar and Q are exactly the same. So it remembers nothing. Okay? Since it doesn't remember anything, I say I will avoid 1, 1. And if I ever do that, my circuit forgets. Okay, let's do that. Let's do that. Let me use a color I have not used so that I don't get it mixed up with this. This is, let's say, 0. This is, let's say, is 0. This is, let's say, it's 0. Okay? Since this is 0, this is a 1. At some time later, R becomes 1. R becoming 1, since there is a 1 here, there is a 1 here, this remains 0. Since there is a 0 here, there is a 0 here, this remains 1. Okay? And then S was 0. Now let's say at a later time this remains, R remains 1, S changes to 1. Okay? The gate that just saw a change is the lower NOR gate, and therefore there is a 1 here. It sees a 0 on the upper input, it sees a 1 on the lower input, the output becomes 0. The 0 feeds back to the upper gate, and then the upper gate sees a 0 on the lower input, a 1 on the upper input, and therefore this becomes 0. The two ones caused my Q and Q bar to become the same. My circuit no longer remembers whether there was a pulse, the positive pulse was on R or on S. And therefore, I say, let's not go there. Let's not set Q and S and R simultaneously to 1. And therefore, you're saying this is invalid input. And therefore, you're saying I put a dash. I'm changing this transition table to a much simpler table, and that is the table on the right-hand side. There is really not that difference between what I have on the right-hand side or on the left-hand side. See, I'm saying if S changes, Q plus becomes 1, whatever it was, okay? Which means these two cases. If R changes to 1, Q plus becomes 0, regardless of what it was. If it was 0, remains 0. If it was a 1, becomes 0. 0, 0. Those are the red cases. Q remains the same, which is this and this. And then 1, 1, regardless of what Q was, stay away from it. Don't do that. Okay? And these are the two black cases. Okay? This is an SR-Latch.